So previously we were looking at the concept of impedance matching, right? So when it comes to the impedance matching using the transmission lines, the method is called as the stub matching. All right. So stub matching is a technique, right, by in which we try to do the transformation of the impedance by connecting or inserting a specific uh, length of the transmission line. It can be open circuited, it can be short circuited, right, between the source and the load. Okay, so anyway, I'll quickly try to explain what exactly we are trying to achieve here. All right, so this is a rough diagram. So let us assume that we have a transmission line like this. So there is a load, and so from this side we have a source coming from this side. Okay, that is a generator. Generator is present on this side, and here we have the load ZL. And you see, if at all this ZL matches with the Z0, then there is no problem. So ZL is not equal to Z0 is our problem. Okay, so it is not matched. Right. Now, uh, let us assume that this is complex, right? Let's assume that there is a Z0, right, which is, say, a real value of Z0, in the sense it is R0. Okay, so let me write it in this way. Uh, let the Z0 be real, right? So that implies I have only resistor value, that is R0. Okay, right? Say 50 ohms, something. Okay, now the ZL will be complex. Okay, you have some R plus, or maybe it is minus, some J into X. Okay, that's what is the value which I have here. Okay, now I have to match. Matching in the sense, for a transmission line, this impedance ZL should look like the R0 value itself. Are you understanding? Right? Only whenever I make sure that the ZL looks like R0, we say that yes, it is matched. So to do that, what we are going to use, right? So right now our concept is a single stub matching. We'll look at only the single stub. Okay, you can even use the double stub for this purpose. Okay, so the single stub matching is a concept where we try to use single one transmit sorry, one transmission line. So let us assume that this is the transmission line which I am talking about. All right, so this is the transmission line we are using, and let's say most of the time, practical case, you use a short circuited stub. So in the sense, the other side will be a short circuit like this. Okay, so this is the short circuited. It's a transmission line, but it is of very small length, so we call it as a stub. Fine. Now what is the design part over here? So before going to the design part, let's look at the requirement. So the requirement is something like, whenever I look into this, right, I should be able to look at the R0. I should be able to look at the value as R0, but it is not actually R0. right? What happens? I'll look at the basics I studied. When basics we studied when we consider the concepts of impedance of a transmission line. So we know that as we move away from the load, right, at every point its impedance changes, correct? So for example, right, let me say I have a value like this is 10 plus j6 ohms. So as I move somewhere here, maybe the impedance looks like 5 minus j8. It continuously changes. That's what is the point. We already have studied that this is what is going to happen. Okay, right, that's the first thing. I'm going to use that concept, right? I'm going to move from the load, that is from this point. I'm going to move such a distance that let me mark the distance first. Let us assume that I'm able to calculate a distance from the load. Let me denote that as the distance L. So L is not the length of the transmission line now. L is the distance I move from the load towards the generator. Okay, I move such a distance, right? Now this L is not a fixed value, it is a variable value, but you stop at a point where the impedance at that point, in this particular point, okay, so in this particular point the impedance means it will have two parts, like one is a real part and one is the imaginary part. The real part matches to the R naught. So this will be something like R naught plus J times X dash. Okay, I'll call this is X dash so that I don't have to call the impedance as X dash. I'll simply call it as J times X. Okay, so the load is X dash now. So just see the change I did. Okay, so see this is X dash. There is a X dash over here. So now the one which we are talking about is simply Jx. It's not real, it is still complex. Okay, so why I did that? Because anyway, I got a real part. This was real and I am matching to that. Okay, but the problem is that there is a plus Jx with that. Okay, so to cancel that plus Jx, what I'm going to do, I'm going to draw the stub length as say L dash. Let me back and let me draw something. So the length of this stub, right, we will be calling that as say L dash. Okay, now this is because we can design, see the stub can be designed to form an inductor or to form a capacitor. Specific length should be selected so that it can work as an inductor or a capacitor. Now, why it is inductor or capacitor? Because you see the concept. If I have a plus jx here, this has to be minus jx. So plus jx is for inductor, this is capacitor. So this will get cancelled. Plus jx minus jx cancelled. Otherwise, if it is minus jx, which is a capacitor over there, this should be plus jx, correct? So it can cancel. So you see, right, I can design the specific, I can actually make the length of the stub specifically designed so that it can match a plus jx by minus jx, or if it was minus jx, I can make it as a plus jx. Is it okay? So when this happens, we say that yes, the uh, the impedance has been matched, because when you look from this side, what happens, this plus jx and here I have a minus jx, that will get cancelled. Only R naught remains. So R naught was my characteristic impedance, and from this point onwards, if you look inside, this whole combination will look like simply R naught. So that means yes, my stub is matched. Sorry, my impedance have been matched to the load has been matched to the impedance of the, or the characteristic impedance of the line. That's what was our motto, right? That's what our was our intention. So we did that so that Hence, we say that impedances are matched. Is it okay? So this is what we are trying to do. Okay, right. So we will look at only the single step, right? So on the Smith chart, we have two techniques to do that. We'll discuss that when we start solving the Smith chart problems, maybe in the next class. Okay, but before that, we need to look at the method that is used to uh, calculate the L and L dash. All right, so these are the two things which we need to calculate now. So let's solve the problem. Let's try to derive the concept first. So for this, for the above set the scenario, that is this particular diagram, right? We'll start with the Z in equation, right? Input impedance, we know that. So we know that. Let's start with the Z in equation. If you remember, Z in is equal to Z naught times this is ZL plus uh, Z naught times tan H of gamma L all divided by this is Z naught plus ZL tan hyperbolic of gamma L. So this is the equation. Now what I do, we don't deal with the Z, but we prefer the admittance method. So converting the impedance into admittance because they are in parallel. In parallel, admittance gets added. Okay. So converting to admittance. So admittance is now that is capital Y y in is equal to this is y naught into same everything remains same but we try to replace with the z naught by y naught yl zl by yl, so they are the inverses of each other. Okay, so yl plus y naught into tan hyperbolic of gamma l divided by this is y naught plus yl tan hyperbolic of gamma L. So why we did this? Because whenever we have resistances in parallel, the equivalent resistance will be R1, R2 by R1 plus R2. So you have multiplication as well as division and addition, three things coming up. But if you do it in terms of admittance, simple addition, correct? So that's why we are doing we are converting everything into Y. Okay, now let us try to write it in another format, that is what is called as a normalization. Normalizing, so normalizing in the sense you divide everything by y naught. Okay, so that is, I'll call it as a small y in that is equal to capital Y in by capital Y naught. So take this Y naught to the denominator on this side, right? So that is equal to, this is the small y in, see the difference. Capital Y in is the actual value, small y in is the normalized value. So everywhere, both in the numerator and the denominator, I divide by y naught. So what happens? This is yl plus y naught cancels. It is simply tan of gamma l divided by this is y naught by y naught 1 plus this is yl into tan hyperbolic tan h of gamma l. Okay, now let us say that we are operating at a very high frequency. Okay, at high frequency, if you remember, what are the changes? Alpha is equal to 0 and the gamma becomes equal to simply j beta. Correct? So therefore, let's write. Therefore, y in is equal to this is yl. Okay, I'll write a yl. So this is yl plus we already have applied this. So tan h of j beta l is nothing but j times tan of beta l, right? So divided by, this is 1 plus yl, uh, j will come out, sorry, j times yl tan beta l. Are you okay? Now it's a complex number. I have a complex denominator, so we have to perform the rationalization by multiplying and dividing by the complex conjugate of the denominator. So that should be 1 minus j times yl tan beta l divided by, this is 1 minus j yl tan beta l. Okay, now let us try to multiply then. So numerator is yl into 1 minus j times yl into yl, that's yl squared into tan beta l, then plus j times tan beta l, and j square is minus 1, so minus of minus is plus, it is yl tan square of beta l whole divided by, in the denominator it is 1, j into j is j square, so plus yl square tan square of beta l. Is that okay? All right. So in the next step, now I'll try to separate the real part and the imaginary part from this. So the real part will be, so I can write the yl into 1 plus tan square of beta l. So that I am actually collecting from here, yl and yl tan square beta l. So I'm trying to take yl common and writing it like this. Okay, so that's the real part. Anyway, real part gets divided by the same 1 plus yl square tan square beta l. That's the first term. Then let me write the imaginary part. So plus j is common. I can try to take a tan beta l also common there. So what remains is 1 minus yl square into tan of beta l divided by 1 plus yl square tan square beta l. Is it okay? Okay. Now, you see here, as we discussed earlier, now I have to get a R naught here, right? At a distance of L, I should get a R naught, correct? So R naught in the sense, let me come back. So now I know that I have this is what? This is the Y in, correct? Now I need a condition. My condition is that the Z in should be equal to R naught, correct? So this implies the Y in should be equal to Y naught, right? So that means capital Y in by capital Y naught should be equal to 1. So that should be equal to my small y in, isn't it? Because small y in is capital Y in by Y naught, correct? So Y in should be equal to Y naught. That is because of this condition. My Z in should match to this one, correct? Right. So that is only this part, right? So the real part is what we are going to use, correct? This is the real part. This should be equal to 1. So that's what is this condition. Y in is equal to 1. Okay. And to design the length of the stub, right? So what should be the length of the stub? I'll use this. Okay. The imaginary part I should cancel. All right. So I'll use that there. So this implies, now let us calculate. So just see what I'm using. So the first term is the one I'm going to use in the equation of yl. So that is equal to, that is yl into 1 plus tan square beta l divided by 1 plus yl square tan square beta l tan square beta l should be equal to 1, right? So move the denominator to the other side. So that means yl into 1 plus tan square beta l is equal to 1 plus yl square tan square beta l. Okay, I'll try to take the terms containing tan square beta l to the same side. So that is yl plus yl tan square beta l is equal to 1 plus yl square tan square beta l. Is it okay? So move the tan square terms to the same side. Uh, yl square. Yeah, so I cannot cancel because there is a yl square. So I'll take the tan square beta l common. I have yl minus yl minus yl square should be equal to 1 minus yl. Okay, the 1 is here, yl is here. I'm moving the yl to the other side. Hope that is fine. Okay, so that means uh, okay, I'll take a yl common here. Yl times tan square beta l into 1 minus yl is equal to 1 minus yl, correct? Because from this I'm taking the yl out. Is that okay? Right. So now you see, I can cancel these two terms. On the right hand side, I'm getting 1 here. So that means tan square beta l is equal to 1 divided by yl, right? So that means tan beta l should be equal to 1 by root yl. Is it fine? So beta l, so let me try to write it in this way. So that is equal to, what is yl? Yl is nothing but capital YL by capital Y naught. So that if you want to write it in terms of the, because y is not available, normally we will be having the z with us. So that will be ZL divided by Z. So tan beta L is equal to that. So beta L is equal to what? Therefore, beta L is equal to tan inverse of root of ZL by Z naught. Anyway, we are fine with that. So now move the beta to the other side, because my intention is to find the location L where I'm going to insert the stub. So L is equal to, this is 1 by beta times tan inverse of root of ZL by Z naught. So even if we want to substitute the value of beta, beta is 2 pi by lambda. So this is lambda by 2 pi tan inverse of square root of ZL by Z naught is the required location. This is the location of the stub. See, from the load, how much distance you should move, where you are going to put the stub. So we derived that the condition. Okay, so whenever we solve any problem, this equation can be used so that you can verify the answer. Okay, that's one thing. So the next part of my derivation should be the calculation of L dash. What is the length of the stub that you are going to put? In the sense, what is the length of the transmission line that you are going to add now? Newly added length, L dash. So to calculate that, what I'm supposed to do here is that, uh, so the susceptance of the short circuited stub should be y minus of y naught into cos cot beta L dash. Okay, so that's the condition. So B So why we are bringing the susceptance? Because first let me write SUSCEPT susceptance of the short circuited stub. All right, susceptance of the short circuited stub should be now let me try to go back. So we already have discussed that there is a plus jx. So this is minus jx, but we are in the y domain. So in y domain, this is susceptance. Okay. So the susceptance I'm going to match should be the should be like this. So that's what we are trying to calculate. Uh, okay, let's do this something like okay, let's go back and check the imaginary part once, because whatever imaginary part we got earlier, we are going to use that here. So that is this term. Okay, so I'm trying to calculate the susceptance, right? So I can try to call this as, because so okay, just recall what we did here. This is what we equated to y naught divided by y in, right? That, right, y in by y naught, sorry, not y naught by y in. We had derived this considering that this is y naught by uh, y in by y naught. So we equated that to 1 and we got the length. Now uh, what I'm supposed to do, I'm supposed to make the length of my stub such a way that it actually cancels the second part. Correct? So this second part I am supposed to cancel, right? So what I do, I start with this to that part of my equation to calculate the susceptance part first. Okay, so I'm going to call that as uh, okay, let's write in this way. So susceptance is denoted by some b, so b naught by y naught. That's what is the right hand side, second term of the right hand side. I'll write it like this is 1 minus, so that is yl square times tan beta l whole divided by, this is 1 plus yl square. It's the imaginary term we got earlier. Okay, I'm just writing that. So tan square beta l. There is no bracket. Sorry, this bracket is not there. Yl square tan beta. Otherwise, the tan beta will cancel. Okay, so I am going to make a substitution that the tan beta L is simply, already we have proved this, that is y naught by yl. So I'm going to put this back. So that is equal to, this is 1 minus, okay, let me make a small change. So previously we don't have the capital YL. I'll write a small YL so that it becomes easier for us to follow. This is small YL. This is also small YL. Okay, now I'll make a substitution. So small YL is equal to capital YL by Y naught. So this is YL square by Y naught square whole multiplied by root of YL by Y naught. Okay, everything divided by, in the denominator also I have plus, sorry, 1 plus, this is YL square by Y naught square into, this is tan square, right? So it is Y naught by YL. So YL will cancel, Y naught will cancel. Okay, now, so I can try to rewrite this in the following fashion. So this is equal to 1 minus, so this can be written as 1 minus YL by Y naught into 1 plus yl by y naught into root of yl by y naught. Okay, because this term is a square minus b square, I can write it as a plus b into a minus b. Okay, divided by denominator is 1 plus yl by y naught. Is it okay? So this and this will cancel. So the term which I am calculating right now is sum b dash divided by y naught. The normalized value comes like this. Is it okay? So that means I can try to rewrite this in the following fashion. So this is 1 minus yl by y naught into root of yl by y naught. Okay, let me try to take left hand side. I have b dash by y naught. Okay, so this can be written as y naught minus yl divided by y naught, common denominator, into root of yl by y naught. Why I wrote? Because this y naught cancels. Okay, so I have the value for b dash. This is what I was looking for, the susceptance, the y naught minus yl into root of y naught by yl. So this is what is the susceptance we are calculating, right? But I should cancel the susceptance, right? So, but the susceptance should be, there we had the, if at all it was z, it is z naught tan beta l. When I take the inverse, it is, right, y naught, z naught becomes y naught, 1 by tan is cot. Okay, cot beta. Now you see L dash. L dash is the length of the stub. So length of the stub should match this susceptance, correct? So that implies on the left hand side, I still have the same thing. This is y naught minus yl into root of y naught divided by yl should be equal to this value, whatever we had written. That is y naught cot beta L dash. You see, L dash is the term which we are trying to calculate. Is it okay? All right. So now let us try to calculate, let's try to simplify this. So we are very close to the answer. Our intention is to calculate the L dash. Is it okay? Right. So cot beta L dash should be equal to y naught is there. So, okay, this is y naught minus yl divided by this y naught cancels with the root y naught. Okay, and I'm going to get a y naught in the denominator, that is yl y naught. So if that is the case, right, cot beta L dash is this. So I can write beta L dash is equal to, I'll convert that into tan. So if you want to get a tan inverse, your term should be reverse. So this is root of ZL Z naught divided by ZL minus Z naught. Okay, take the inverse, that's all. So denominator goes to the numerator, numerator comes to the denominator, you get a beta L dash, right? So simply calculate L dash. L dash is equal to 1 by beta. I know that 1 by beta is lambda by 2 pi. Okay, lambda by 2 pi into tan inverse of root of ZL Z naught divided by ZL minus Z naught. So you know the values of ZL, Z naught and the lambda value, you can calculate the length of the stub required by using this particular equation. Okay, so that is a complete derivation which helps us in finding out first L, the location of the stub from the destination, from the load, and L dash, which is the length of the short circuited stub required to match the susceptance of the load.